points if you think about that this is something that we measure in the continuum. Okay? So as long as I have a very, very, very precise instrument, I can add as many decimals to my measurement of height, and that's why we have this infinite possible numbers of height values. So we will see that in that case, for continuous variables, we won't have finite probability models, but instead continuous probability models, and we're going to talk about that in a second. But for these examples about rolling 2 dice, flipping a coin, the example about the mother tongue, these are all examples of finite probability models. So, what else? Yeah, so we need then to be able to assign probabilities to each possible outcome. So each probability must be a number between 0 and 1. And then when we add the probabilities of all possible outcomes, it has to sum to 1, right? So if these 3 things happen, then you can say you have actually a probability model. Otherwise, you don't have. Okay? So we can actually check that when you see some outcomes and some probabilities associated to these outcomes, we can actually check if that is an actual finite probability model or not. Sometimes, instead of calling finite probability models, we also call them discrete probability models, thinking about that the type of thing that we are measuring is discrete. It has these discrete values, okay, associated to them. So it's not in the continuum. Right. So here's an example. So we have, these are the first digits of numbers in financial records. They often follow a model known as this Benford's law. So here we have all the possibilities for the first digit. So 0 is not a possible outcome. So it has to start from either 1, 2, 3, 4, 5, 6, 7, 8, or 9. So we have these 9 possible outcomes. And then this law, this Benford's law, gives these particular probabilities to each possible outcome. For example, the probability that the first digit in the record is 1 is 0.301, and then for 2 is 0.726, and so on. So now I can check if this is actually a finite or discrete probability model. So the first thing I need to check for is if each probability is between 0 and 1. So when I look at the numbers, yes, so we're good to go. So now we can check if I sum all of them, I get 1, and that's the case. Okay, so then I can actually say that this Benford's law is an example of a finite probability model because it follows the rules of a finite probability model. Now, if I want to find the probability that the first digit for the chosen number is not a 1, so I can use that last rule of probability. So the probability of not being a 1 is just 1 minus the probability of actually being a 1. So that gives you 0.699. Okay? Now let's see this other example. So again, this is one of the exercises in the end of the chapter. And for this one, you don't have an answer because it's an even one. So it's about cups of coffee. So we have 5 different possible outcomes for the number of cups of coffee someone drinks on a day, on average. So we can have 0, no coffee, that's not me, 1, 2, 3, or 4 or more. So the person has to pick one of these, okay, one of these possible outcomes. And then here are the probabilities associated to each one of the possible outcomes. Now, the first question is, can we check that this is actually a finite probability model? So again, why finite? Because I have a finite number of possible outcomes, and I can actually enumerate them. So I have 0, 1, 2, 3, 4 or more, so 5 possible outcomes. So what I should check for? First thing, I should look at each individual probability and make sure that it is a number between 0 and 1. And that's the case. Now, if I sum all these probabilities, do I get 1? If yes, then it's a finite probability model. Now, what is the event x smaller than 4 in words? So we're calling x the number of cups of coffee you drink per day. So that's x. So what would be x smaller than 4? Anyone? What is this event? How can you explain that in words?
I don't know exactly, but you calculate how much is in the other categories other than the 4 once you add all those up, or you can subtract that by the total, which is 1, or the 1 minus the 4.
Yeah, so that would be already calculating, right, the probability for x being smaller than 4, but the event x being smaller than 4, you could describe that as drinking less than 4 cups of coffee per day, or drinking 0, 1, 2, 3 cups of coffee per day. Okay? Either way. And then the probability for that, we could just sum up all the probabilities up to 3. So it would be 0.36 plus 0.36 plus 0.13 plus 0.08. Or, what would be another way to do that? Yes.
1 minus
Yes, 1 minus probability of 4 or more. So you could do just 1 minus 0.11 as well. Okay? Now, how I could express the event, now in terms of x, right? Now it's the other way around. So in part B, I showed you the event in terms of x. Now I'm giving you the sentence and I want you to express the sentence in terms of x. So the sentence is, have at least 1 cup of coffee on average a day. So how could I express that in terms of x? So what would that be in terms of x? So x greater or equal than something, x, I don't know, smaller than something. How can you express that event in terms of x greater or equal or smaller? Anyone? So at least 1 cup of coffee per day. So what would that be? Yeah, so you can do x greater or equal than 1, or another one, x greater than 0, right? Okay, because it does not include the 0, so it has to be 1, 2, 3, 4, and more. Okay? Either one. And then what is the probability of that event? Anyone? Yes. Yeah, so you basically do 1 minus the folks who never drink coffee, right? So it could be 1 minus 0.36, so that's going to be the probability of drinking at least 1 cup of coffee. The other way is to sum the probabilities, so you would sum the probability under 1, 2, 3, and then 4 or more. Either way, okay? So let's see. So just checking that it's a finite probability model for part B. So that's the event in which an individual drinks fewer than 4 cups of coffee on average per day. That means it's the individual who drinks 0, 1, 2, or 3 cups. So, yeah, so now for part C, so you can write it this way, right? Or you could also write greater than 0. That's okay as well. So that could be written as 1 minus 0.36, which is actually 54, right? I don't know why I put 0.6 there. Approximately, I guess. Okay, please correct that. I will correct mine later too. Okay. All right, so now we're getting closer to talk about the Gaussian curve again. Yay, we're going to see it in a minute. So remember, if we don't have something that is discrete, that I can actually enumerate and have this fixed, limited possible number of outcomes, so if we are working with things in the continuum, for example, time, height, weight, I don't know, blood pressure, temperature, there are so many things that are not discrete around us, then we need a continuous probability model. So in that case, we are not able to assign probabilities to any individual outcome, but we can talk about probability over an interval. So I cannot assign, okay, I want to know what is the probability for all possible heights of students at Western. I cannot give a probability to each individual value, actually because it's 0. I will show you why. But I can talk about an interval. I can say, okay, what is the probability of students at Western having heights between, I don't know, 160 and 170 centimeters? That I can do. I cannot talk about individual values. Okay? And now, to describe then this model, what I need that density curve, I need that distribution, this probability distribution. And remember, when we talked about the normal curve, we already know that the area under the entire curve must be 1. Okay? So let me show you an example. I guess it's easier. So another example of distribution that we can use instead of Gaussian is the uniform distribution. So remember, the uniform distribution is just this rectangle, right? And then the idea is that we can compute basically the probabilities of any interval is just proportional to the size of the interval then. So it's more or less like you're giving the same probabilities across this interval, right? So if you have an interval of size 0.2 here or size 0.2 there, they will both lead to the same probability at the end of the day. So when you have a uniform distribution, then again, we can talk about probabilities over an interval. So if I want, let's say, what is the probability of a value smaller than 0.5 or greater than 0.8? I just need to sum these two blue areas. And because it's a rectangle, I know how to calculate areas. It's very simple. I just do the width times the height, right? And then it gives me the area for each one of them. And then I can just sum the two. Okay? Now, in the case of a normal curve, a Gaussian distribution, it's a little bit more complicated to calculate this area because it involves that complicated formula for the normal curve. But luckily, we have that table in the end of our textbook, and also we can use software to compute any area that we want under this curve. Okay? We also know, for example, that below the mean, we should have 50%, right? And remember, we also know the 65, 95, and 99.7 rule based on the standard deviation, how far you are from the mean in terms of standard deviations. And then outside that, I can still compute the area corresponding to any interval using software or doing the Z-score and using the table at the end of the textbook. Okay? So normal distributions, or the Gaussian distribution, the normal density curve, these are continuous probability models. So we can model things that are continuous using the normal curve. So this example is about height, because I mentioned that to you, right? Height is one of the things in nature that they happen to be normal. So if you take the height of many people and you draw a histogram, you will see that it follows a bell-shaped curve. So this example is about height then. We're looking at the height of all young women, and they follow a normal distribution, pretty close, with this mean of 64.1 inches and then a standard deviation of 3.5 inches. So once you know this, once you can approximate the distribution of this particular random phenomenon, which in this case is the height of young women, now we can use that to calculate all sorts of probabilities over different intervals. For example, what is the probability that a randomly chosen young woman has a height, and I can call height X, right, between 68 and 70 inches. So if you have a software in front of you, you can just go ahead and then ask the software to compute that for you. But if you don't have a software, you can use Z-score, right? So you can basically transform your X into Z. So you can bring your variable from this particular normal to the standard normal, because usually we have tables at the end of textbooks about the standard normal, about the Z's, not about the X's. So you have to standardize to get the Z-scores corresponding to these values. So one is 68, the other one is 70. Remember the way we do the value minus the mean that you're assuming for the normal. In this case, 64.1, and then this divided by the standard deviation you are considering, which is 3.7. So if you do that, now instead of working with an interval over the axis, now you have an interval over z's. And now you are interested in this area between so to draw your normal curve. So you are interested, this is 0 because the standard normal has a mean of 0. So you are interested in calculating the area between 1.05 and 1.59. Yeah, so it's a very small interval, right? Let's say we're interested in this area here. Okay. So now what you can do, remember the table only gives you the proportion or the area up to a certain value. So if you want to get this area, so what you can do then is, so you have to actually do two things. You have to do the area below 1.59 minus the area below 1.05. Okay? And then that will give you exactly what you want left. is this small area here. Okay? So let's go back to things we already learned in chapter 3, 4, don't remember anymore. Okay? So then you can look at the table for the proportion corresponding to this value, proportion corresponding to this one, and then what you get is approximately 0.09. Okay? As I promised you, and I told you that the whole thing about calculating proportions from a density curve, from the normal density curve, it would show up again. So it's showing up again. Okay? Cool. So this is what I was trying to illustrate with my bad drawing. So the 1.05 and the 1.59, they correspond, right, to the 68 and to the 70. It's just that I went from this particular normal to the standard normal in order to use the table at the end of the textbook to calculate that proportion. Cool. So let's take a look at this example now. Adding random numbers. This is pretty interesting. So if you generate two random numbers between 0 and 1, any number could have many decimals actually. It could be 0.55, 0.9111, whatever. So you generate two random numbers between 0 and 1 with as many decimals as you want. And you take the sum of them. So the sum of them now will be any value between 0 and 2, right? That's the max that you can get is 2. And the minimum would be 0. If both are 0, they will sum to 0. But it's continuous because it can be actually any value between 0 and 2. So what else? Yeah, so it's interesting that the density curve that you can get, let's say the distribution, you could do a histogram of these values after you sum these two numbers. You're going to see a triangle. And it's pretty neat, right? So, yeah, and I'll show you that that's the case. I shared with you a Python example doing that so that you can trust me. That's the case, okay? So when you sum then these two random numbers between 0 and 1, the type of density curve that you get is this triangle where the base is of size 2 and the height is of size 1. Now, I'm asking you to verify by using geometry that the area under this curve is 1. So basically, it's just the area of the triangle, right? And then I want you to calculate what is the probability that x is less than 1, and then sketch the density curve, shade the area that represents the probability, and find that area, and then do that the same thing for part C. So part C is what is the probability that x is less than 0.5. So we can do all this using geometry. So for the area under the curve, we have to check if it's actually 1, and it is. So we just need to use the formula to calculate the area of a triangle here. So it's going to be the base times the height divided by 2. So in this case, the base is 2, the width of the base. The height is 1. When I divide by 2, I get 1. So we're good to go. So we do have a probability model. So we have a continuous probability model for the sum of two random numbers between 0 and 1. Now, what is the probability then that x is smaller than 1? Okay, I can just, by just drawing, I don't actually need to do any math because it's symmetric around 1. And then if the area under the entire triangle is 1, for half of it, it has to be 0.5. That's okay. You can justify that by just drawing and shading the area corresponding to a probability of x is smaller than 1. And then by symmetry, you can just tell me if it's 0.5. It has to be. Okay. Now for the last one, I want the area of this smaller triangle here, shaded in gray. Okay. So now for that one, again, we're going to consider the area of the triangle as the base times the height divided by 2. But I have to be able to see that the height here corresponding to 0.5 is actually half of the height, the original height. So once you see that, then you're good to go, because now you know that that height is 0.5. Okay, and then you just do 0.5 times 0.5 divided by 2. So the probability is actually 0.125. Yeah, so this is what I meant. So I added this example together with the slides for this chapter under resources on how. So what I'm doing, I'm just generating uniformly numbers between 0 and 1. So I did 1,000 of them corresponding to number 1, right? So 1,000 numbers, another set of 1,000 numbers, and then now I sum them, the first plus the second. So that gives me another object that I call x. So x here is the sum of these two numbers, okay? So I have a vector actually. So I have 1,000 numbers here, 1,000 numbers here. When I do number 1 plus number 2, it's doing the sum by each entry of the vector, right? So it takes the first entry of the vector number 1, and then it adds with the first entry of number 2, and so on. And I'm even showing you the first 5 sums. So these are the sums. Again, they can be any value between 0 and 2. So we got like a 1.05 here. Now if I do a histogram of this, as you can see, I'm showing you 1,000 sums, right? You kind of see a triangle, but not quite yet. But if I increase the sample size, right, then it will become clear. So now I'm just doing like 100,000. So I draw 100,000 numbers between 0 and 1, sum both of them. So now I have this x is a vector of size 100,000. Now if I do a histogram of 100,000 sums, there you go. So you see the triangle, right? Yeah. So again, remember that the idea of the density curve, we are trying to approximate the distribution. So, and therefore, as we increase the sample size, if I make it bigger, 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 at some point you will see a perfect triangle. Okay? That's the idea. At some point you would see a perfect triangle like that. So what is a random variable? So a random variable is a variable whose value is a numerical outcome of a random phenomenon. So nowadays, if you want to ask that question, then we're actually going to see the numbers, right? So, for example, when we talk about flipping a coin and getting a head or a tail, we can assign numbers to those outcomes. And we need numbers because in the end of the day, we're going to be doing math and we need numbers. So usually what we do, we can assign a head the number 1 and then a tail number 0. Or we could also do a head 2 and a tail 1. So it's really up to us how we define things, but we can assign numbers to our outcomes. When the outcome is already a number, then you don't need to do anything else, right? So if we're talking about the height of students, height is a number already. If I'm counting, let's say, how many cars are parked in the parking lot behind us here, so that's already a number. I don't need to do anything. So it's more when we have categorical things that we need to assign then numbers to them. Okay. What else? So the probability distribution of a random variable x tells us what values of x can take and how to assign probabilities to those values. So when we have a random variable that is discrete or finite, then we're going to have like a finite probability model that is going to contain this probability distribution, which is going to be discrete as well. But then when we have a continuous probability model, we will have like a continuous probability distribution then. We're going to have these density curves, for example, the Gaussian or the uniform. What else I want to say? Yeah, so we have the finite or discrete random variables when we can only have a finite list of possible outcomes. And then we also have the continuous random variables when we are actually measuring things in the continuous. And then when the probabilities can only be described in terms of areas under this density curve. Okay. What else? Another exercise, so we can do this one together as well. So let's see what is this one all about. So we have grades in a business course. So we have different categories of grades. So it could be A plus, A, and then A minus, B plus, and so on. So we choose a business student at random. To choose at random means we give every student the same chance to be chosen. The students grade on a 4-point scale. Yeah, so these are the grades corresponding to each letter. It's a random variable with this probability function. So we have all these possible grade values from A plus all the way to F. So each entry here then corresponds to one of these possible grade categories. And then we have the probabilities assigned to each one of them. So is X a finite or a continuous random variable? Anyone? So I would say before you actually categorize into A plus, A, and so on, when you take the grade as it is, it's continuous. But then after you use the A's, B's, C's, and so on, then it's finite now. Because you only have a certain possible number of categories. So that's what we do. So X here is finite and discrete because it's actually considering the categories according to A, B, C, D, and F. Okay? And then you have a sample space that is finite. You can enumerate all of them, and there's a fixed number of possible outcomes. What is the second question? Say in words what it means for X to be greater or equal than 3. So that would be to get a grade corresponding to let's say B, right? A B plus, or an A minus, A or A plus. Okay, so it will be 3, 3.3, 3.7, 4, or 4.3. So it will be a grade greater than B or greater than B, at least B. At least a B, or earn the B or better. So it has to be B, B plus, A minus, A, or A plus. So if you sum all of those, that gives you 0.60. Now write the event the student got a grade poorer than B minus in terms of the random variable x. So B minus corresponds to a 2.7. So if the student did poorer than that, so it means that it has to be P of x is smaller than 2.5, right? 2.7. Okay, that's the event now in terms of x. And now to get that, you can sum the probabilities corresponding to all events that give you a grade smaller than 2.5, which would be the C plus, C minus, D plus, D, and D minus, and F. And some of these probabilities are 0, which can happen. As long as it's a number between 0 and 1, including 0 or 1, that's okay. So, here's one more. Okay, let's finish this one. So running a mile. So a study of 12,000 male students found that their times for the mile run were approximately normal, with a mean of 7.11 minutes and a standard deviation of 0.24. Now we choose a student as random, and we call this time for the mile run y. Y is my time for the mile run. So is y a finite or a continuous random variable? So in this case, we're measuring time. So it's continuous in its essence, okay? So it's a continuous random variable. Another hint is because we consider a normal distribution associated to those times. And remember, if we're talking about normal distribution, it has to be about things measured in the continuum as well. Now, saying words what it means by probability of y greater or equal than 8. So that means the probability of a student taking 8 or more than 8 minutes to run a mile, right? And then what is this probability? So I can use now the normal approximation to calculate that. And one way to do that is recognizing that the probability of y being greater or equal than 8 is equal to 1 minus the probability of y being smaller than 8. Again, because the table that you have at the end of the textbook only gives you proportion smaller than a number, right? Below a certain number. So that's what I mean. So you can do this. If you have a computer, you could do this right away. But if you only have the table, then you have to compute the z-score corresponding to this 8. And then you have to do 1 minus that in order to get the actual probability that you want. If you're going to use the table 8 at the end of the textbook. Now the last one is write the event the student could run a mile in less than 6 minutes. So that would be y has to be smaller than 6, so probability of y is smaller than 6. And there you go, the same idea. You have to compute the z-score associated to the 6. Now you're good to go. Because this is the probability of something being smaller than the number. And that's exactly what the table gives you. So you can just go ahead and look at the table. You don't have to do the 1 minus. So you should try to reproduce these things. Look at the table, get these numbers, because again, this will show up again in your final exam for sure, 100%, right? So we already saw this before, we're seeing this again, so it's very important that you know how to compute proportions, probabilities using the normal density curve, okay? Another comment, I just want to say, I forgot to mention that about the exams. So we noticed most of the exams, the answers were not organized at all. It was very hard for the TAs to find where the answers were in the page. So as you practice for the final, you should, of course, practice your timing so that make sure you can finish the exam on time. Now that you know the formatting, so try to practice reducing your time, right? Something like that. But also practice to write down your answers in a very nice way, organized, and so on, okay? Because you have to think the TAs are grading thousands of questions, so they're not going to be looking everywhere in your page to find your answer. So practice writing things nicely, okay? As much as possible. I want to see beautifully written. Okay? So that's it for today. We're going to see more examples on Thursday. I hope you see some of you bring up the